Okay, so this part here I will talk a little bit about user interfaces for finite element applications, and especially for exploring forms and structures in different ways, and how you can take advantage of the new hardware that you have in your computers, and how you can design your user interface a bit differently than before. So, general theme is computational tools in architecture engineering. So, you probably have seen this, or at least in your own application, the classical simulation cycle that you have. You define your geometry, you add your forces and boundary conditions, you define your materials, you run your simulation, you look at the results, and then you go back again. And usually many of these parts in the applications are discrete steps that you have to go through. And you lose the connection between the results and then going back and doing the updated geometry. So for example, in a classical way, this is similar to what Pierre showed you here for a classical two-dimensional finite element application. This is an application called HACON, which stands for hardening concrete. So it's an application that can simulate concrete during the hardening process. So the energy development and if you need cooling pipes and so on. So here you define the geometry in the mesh. Next step, you define your materials. You have a ground here, different ground properties. You define your boundary condition. In this case here, you can define the temperature outside during a time period. And then you do your calculation. And sometimes this can take a long time, especially, for example, if you have three-dimensional problems, it can take hours to compute. And then you get the results. And when you get the results, you kind of, okay, this was not really good, and I want to go back again. And then you change here your geometry, and you repeat it all over again. But it's kind of hard to go from this and back again. So there's something here that interferes with the engineering process. So there's a lack of feedback between modeling and visualization. There are discrete computation steps that interferes with the design process. And it's also difficult to use when you're discussing with colleagues or clients. So sorry, you have to wait 10 minutes before the calculation is done. And also it's also just difficult to understand behavior because you have to wait so long before you get the results back. So is there a solution for this? Maybe. So what if we remove this discrete computation step? So let's see if we can put the programs next to each other. So this is just a concept here. You have the model on one side, you have the results on the other side, and you change something on the left side, and you can see the results on the right side directly. You have instant feedback, you have better understanding. You can also encourage exploration. So you can do stuff like, what if I change here, what happens on the right side? What happens in the results somehow? Of course, this has some kind of, you need to kind of change the way you do your applications a bit differently. So before we go into the solution here, I want to just give a brief history of computer theory. And you got some of this in the last lecture with HPC, high performance computing. So if you look at the computer, the classical model, you have a computer with a single CPU processor. And what you can do with that, you can run a single task on that processor. If you have a computer with multiple CPUs, which you actually have, everybody has multiple CPUs in their computer. You can do multiple tasks simultaneously. The problem is that most of our computational programs are designed in discrete steps like this. So you have modeling, you have computation, you have visualization, and perhaps we need to change this to kind of make it more suitable for using multiple cores. So one way of doing it is to kind of stack them together on top of each other. So having discrete tasks instead. And computation, we have a lot of them. So why not do computation in the background all the time? I mean, we can see if the model is not stable, we don't do a calculation. But as soon as the model is stable, we can do a computation. And we can do it in the background, and we change things, we can send it in the background and do calculation again. And the trends today is that clock frequencies in our computers, the speed of your computer, how fast they are kind of not increasing. But what is increasing in your computer is that you get more and more cores. So it's not, I mean, in a normal Mac today we have 8 cores. So 8 simultaneous tasks that you can do at the same time. And also accelerators like the graphics card you have sometimes have 500 to 2,000 cores per accelerator. So you have a multi-teraflop performance on workstation hardware, and a bit less on mobile hardware, but it's kind of evening it out. Apple just released the M2 iPad. An M2 chip is almost a desktop performance, and it has a lot of cores as well. So what can we do with this? So we can do many complex finite element simulation almost in real time. You can, with multi-core machines, you can do continuously performant calculations in the background. You just discard the ones that don't work or not stable. And what you can do with that is you can model, the models can manipulate in real time on your computer, and you can get direct feedback with that. And that also leads to explorability. You can explore your models. You can try out different things and you get immediate feedback on them. So one solution here, or one kind of applications is the direct manipulation explorer interfaces and computational tools. And at Structural Mechanics, we have done some research on this and also developed some applications that implement these ideas. So the touch concept to kind of work with touch on your computer, it has increased with the introduction of iPad, iPhone, and Android. And most of your PCs today, at least the Windows-based machines, have a touch-based interface on the screen, so you can touch your screen. And the things which kind of, compared to the mouse, the touch interface often requires that your application should respond directly to the touch. You should, if you move something on the screen, you should see the movement on the screen directly. You shouldn't have to wait. You can adapt existing mouse-based applications, but you still have this kind of disconnect with the mouse movement compared to moving your finger directly on the screen. And so to implement this, we have divided up the simulation cycle in different smaller cycles. So you when you work with a geometry, you kind of simulate and visualize results all the time, and then adding force, and you have the same kind of small loop that does all the steps at the same time. Also, when you apply materials, you simulate and visualize results directly. So instead of going kind of step by step, you always do the simulation in the background. And you can move around between the different stages in your application seamlessly between these steps. And you always get results if the model is stable and can give you results. So this is an example here from the force pad application that we have developed at Structural Mechanics. You can see here that if you rotate the force, it calculates directly. So you can get a very nice view of what happens if you move a force in a beam. Now this is a bit old video. Today will probably be very much more smooth because the computational power in your laptop is bigger. So possibilities, you can interact directly with models. You can do direct conceptual model. You can have an iPad. You can talk with a customer, and you can move the things directly on the screen. Also, touch has a benefit that you don't have to have any input devices. You can just use your finger. And you can also have, if you have a larger touch-based surface, you can have multiple users on the same surface. So the first application we developed at Structural Mechanics a couple of years ago was ForcePad. And ForcePad is a two-dimensional finite element application. So if you're doing the stress problem in this course, it's similar. So it's the same, but it's a perhaps bit bigger model. The idea is that you draw with stiffness. So white is no stiffness, black is the maximum stiffness. So, and also the idea was to implement it as a drawing application. So you should use the same tools that when you use a paint program like Photoshop or Paint.net or any of those. So it comes with the same. The user is kind of used to working with those applications, and it also supports this that you can do a sketch, you can refine, you can iterate, and go through this iterative design process in this application. And also, many of the normal finite element, they use this geometry model that we actually use in this course to describe parameter model. But this application uses discretize the finite element from the image. So it goes from an image model to a finite element model. So this is the geometric model. You have curves and you have an element mesh. This is what you're doing in this course. And it's very good for doing parametric models and engineering things. It's a bit more complicated if you want to do design, because you have to redo the geometry, define the nodes, and create curves. So in ForcePad, you instead go from a pixel image, that can be anything. You add your boundary conditions, and then the final step, you go to a finite element mesh that basically creates a discretization from the image and calculates the stiffness. If the element crosses an image, it kind of interpolates and gives a grayscale in those parts instead. But it doesn't. The only thing you have to do is put the boundary condition on the load, and the other geometry you define by drawing, just like a painting program. So here you can see some of the ideas here, that you have the elements in the background here, and you can see how it calculates the stiffness for each element depending on how much coverage of the pixels you have for each element. And of course, if you reduce the grid step, you can almost get the same, so each pixel becomes an element. Of course, that takes a lot of computational time, but you can do that. Another thing that ForcePad can do is you can have a starting image, and then you can give it some criteria on how to optimize that load case, and it can remove material where it's not needed, and you can iterate over it, and you can go from a black block of stiffness to a structure. There are some steps here that you can go back and forth with. You have a sketch mode where you do the image drawing, and then you have a physics mode where you do the boundary conditions and the loads, and you have an action mode where you can do where you can see the results, and you can switch seamlessly between all these modes, and it automatically does the computation between these modes. Here are some examples that we have when we have used ForcePad. So here you start with an image, and then you can extract the important parts, and then quickly create a model from those from an actual image. Here are some other things as well, where they scanned a real structure and imported it into ForcePad to really quickly do a computation. So here is, you very quickly come to a model that you can compute without doing a lot of the geometric modeling and mesh generation. It just goes from image to finite element model. So let's see if I can run a demo. So ForcePad is available in the Windows App Store. I think you can download it for Mac as well. I'm not sure. But so here you have image surface here. So this is our drawing surface here, the paper. you can select brush here, and then you can draw like this. And you can select, for example, if you want to draw with less stiffness. Okay, doesn't work today, so we skip that. But in principle, you should be able to draw in different stiffnesses as well. You can also use geometric circles here to draw ellipses like this. And you can also flood fill if you want. So let's remove this here. So this is like a normal drawing program. So, and then the next step, if I go to the physics mode, and here you have two choices here. You can apply loads and you can apply boundary conditions. So this one here is a boundary condition here, and this symbol means that it's like a roller. So the structure can move in this direction, but not up and down. And if we want to lock it in both X and Y direction, we can put another constraint in here. And just you can see I can change the direction here. And we can put one here on top here as well. Then you can go to the load mode here, and you can also activate here if you want it to take into consideration the self-weight. You just use weight here. That means that it will use the self-weight here automatically. So now we actually don't have to have a load. We can just do calculation here, and you can see here you can see the stresses in this is the principal stresses in the structure. But you can also, if I uncheck this one here, I can put the load here, a normal load, like this. And I can calculate here. I can look at the von Mises stresses. And this is the principal stresses. I can look at the deflection, like this. And I can also see what happens if I rotate the load. So if I just click the load here, you can see here that I can explore here what happens if I change the direction of the load. You can see the reaction force is changing. You can also, it's kind of a spring here. So if you look at the deflections here, you can see here that it moves like a spring, like this. I can also move the load. So let's see if we just rotate it like this. I can move the load here around the structure and see what happens here. So you can see if I move here, this kind of becomes inactive. And I can move it back here again. So that I can also zoom in and see here the principal stresses in the structure. One other thing you can do with this program is to, I talked about this optimization problem here. So, for example, if I have it's not that I wanted to do. I do a block here, like this. And then I know I have some constraints here. I have a constraint here. I have a constraint here. And then I know that somewhere here there is a load that has to be applied. So let's see here if I put a load here. No dead weight, just get there like that. So you can see here now that I have a force. It looks something like this. What I can do now, I need one more constraint here, like this. Now you have a tension here and compression here. But what I can do now is I can use an optimization tool here. So I can ask ForcePad to see, okay, can you come up with a most optimal solution here? And you can set here that you should remove half of the material. press stop here. So now it removed structure that wasn't needed. I can go back here and I can reduce here to, let's see, 30%. You get the thinner structure. There are some parameters that makes the model more stable, but you can see here it becomes more refined. You get tension here. No, sorry, compression really defined here, and tension here really defined on top here. And you can look at the stresses here as well. So this is an example of an application that tries to kind of reduce the computational times and give you a much quicker iterative cycle. You can go back and forth, and you can go back again to this part here, and you can copy it back, and you can work on that. Sorry, I forgot to copy it. Let's see if it'll run again. This one, I will just increase it a bit like this. Yeah, you can click here and then you can transfer structure to image. Then you can go back again here and use this as input and modify the structure again. So I use the optimized structure, and I can add stuff to this here as well. Oh. And I can do the computation again here. So this is just an example of the force-bed application. Yeah, so conclusions here, you can do finite element can benefit the architecture and the structure designer if we use the iterative design and implement that in the user interface. And also the imaging metaphor is well aligns with how designers and architecture works, that you can quickly design sketch something and get a result back quickly. Yes. Objective frame is another application that we have developed, and it's a three-dimensional beam program, and I will look something like that. I will show you a demo later. This application was designed to to enhance the understanding of three-dimensional structures. So it's a 3D beam truss analysis tool, and it has also been used as a test bed for developing new concepts for user interface in finite element applications. It's a C++ application, so this is not Python. Implemented using OpenGL, which is the hardware accelerated graphics API. It uses the Eigen matrix library, which is a really nice matrix library for C++ that's very similar to NumPy. It uses a InGUI user interface toolkit, which is a bit different because it draws all the time. So when you're using Qt, your application is in a window, it's static, you can move it around, but really nothing happens here. But InGUI it will draw all the time, just like when you're playing a game. It's 60 frames per second all the time. It's open source, so if you want to compile it, you can download it and build it yourself, modify it. And it supports also real-time interaction with models. So you can do animation, you can put your virtual finger on the model and see what happens if you move the force. It has also, like Pierre said, you can have, there is an API for controlling application from Python. You can also have write plugins for providing models that are parametric, that you can give some quick parameters and it will generate the 3D model. It can also export the model to Colfem. So when you are done with your modeling in Objective Frame, you can save it as a Colfem model. Yeah. And also we did some couple of years ago before VR. We had a way of we had a special sensor you can put on your keyboard, which sensed your hands, and then you can actually put your load the finger and actually interact with the structure in real time. So let's see here. So this is how objective frame looks. It's a bit, because my screen has a strange resolution here, it's a bit. We have a starting model screen here that you can select some predefined models. So let's try this one here, and you can see you can rotate it here. You can zoom. And you can do calculations here. So now it just calculates the singles for this load case. You can also see here that it visualizes the reaction forces here. And if you zoom in here, you can see that because there is no, it's bars here, so it's not beams. So you will not get any rotational moments here in the bottom here, because it's all bars. So this is a bar structure. And you can also animate the deflections. You can also select let's see here, I can take a beam like this. You can see here the load on it. And let's see, I can just. Yeah, so this is with a static load case. But what you can do with this application as well is to, let's see here, I can check this one here. So I can put a virtual finger on this structure here. Let's see if we can just, and I can move it around. And you can see here that this is a beam structure, so you can see that it visualizes the reaction forces here in real time. And you can also, if you select a load here, let's see if I can do this one here, and you can see here that a bit scaling factor is a bit different, but it automatically calculates the section forces in real time when you move the load around. You can also visualize here the normal forces in the structure, and you can also see what happens when you move the loads around, how tension and compression is changed. You can also visualize moments. It's not so intuitive, you can see where you have moments in the structure. And then you can do, for example, if I want this to be exported to CalFem, I can do save as CalFem. Let's see here if I can see where I saved this here. And you can see the extension here is Python. So let's see if I can find it again. Where did I save it? Okay, let's try it again. Save as CalFem. We'll do it here instead. Test. So you can see here that we recognize the column here. This part here you can ignore. It's the binary description of the model. But what you can, if you go past that one here, you can see here that you have element properties. You have some beam mimics. You have the EDOF for the beams. You have the coordinates. You have the bars, the degrees of freedoms. So you have all the things that you need, and it actually also generates a solver for you. And my computer is slow now because it does a bit too much at the same time now. So if we go test solver, you can see here that it creates a solver. So it imports some tools that you need, and then it imports the model, import test as model. And then you can see here it creates a beam solver with a model attached, execute the solver, and it visualizes results here. So you can go from a three-dimensional model here to something that you can calculate in CAD as well. Another thing it can do is that you can really, let's see here, new project, create. So it has plugins here which you can write yourself as well, but you can do, for example, node grid. No, sorry, I will do regular frame. So here you can see I can 4 by 4 by 4, the distance between the nodes, and then I just click here, and it will create a three-dimensional model for you. You can do also model create. Let's see here. Talk stool or truss, and you can build a house like this, and you can change the parameters here to have let's see, I want to be 6 meters instead, and then I can just do, you can see it's a bit bigger. So that was objective frame. So we go back here again. Sketcher frame is another application that we did in the same manner, and to see if we can implement finite element simulation on an iPad. At the time we did this, the iPad was kind of restricted in the performance. It was not as high performance as a PC at the time, but we wanted to try to see how far we could go and to create a conceptual tool for use in education, communication, discussion. So the idea was to kind of have something where you can imagine an engineer talking with a client, an architecture, and everything, and you want to kind of discuss the design, and to have something that you can quickly create a truss or a frame and investigate how you can use it. So it uses direct manipulations. You use your fingers. It is a 2D frame and truss analysis code. So now we are talking beams and bars. There is no simulation button. So it will simulate or calculate every time there is a stable model. If it's not stable, it actually visualizes the mechanism that you create. So it only simulates when the structure is stable. And by default, hinge beams are created, so they are rotationally, you can rotate around the nodes. And the user can add rotational constraints. You can fix a node for rotation as well. I will skip this one here. Let's see if I have a demo here. Okay. We also did this. We used a smart board to do the same thing with force pad, to kind of have a large force pad, and where you can use your fingers to draw. So that is also a similar way. So let's see here. This is an example of how the sketcher frame works. So here you don't see the finger here, but basically you draw with the finger to kind of draw small beams. So you don't create the nodes by themselves. You kind of draw out, and it will, when you release the finger, it will add a node. So it's a bit different model. Also, if you draw between the two nodes, it will create a bar or beam. And here you just draw between those like this. Unfortunately, we have no new version of this, so it's not available in the App Store yet again. But I'm working on recompiling this again. And then you put your constraints, and then you put the load, and you can see it now directly calculates. So now it has everything to enable calculation. Then you can, with your finger, you can move the load around and see how it deflects. And then you can see here that it's, let's see, here is, and now here you can see the forces when you move the forces around, just like we did with objective frame. You can add loads. And you can see there is no calculation step. Every time you do it, it's immediately updated. And now we fix the rotations of the nodes. So you can see that they become squares, and now they are fixed in rotation. You can also see that the structure becomes more bent here, and you can see these are the moments. And you can see the completely different behavior of the structure now. Yeah. So this was Sketcher Frame, and I hope that we can have something ready again this year. We can update it to be more, because Apple changes their APIs all the time, so we need to, it's hard to keep up. Yeah, so something we're working on here as well is to create a real-time engine for finite element applications. Integrate more advanced models. So now we have a linear model here, so it's static. So it's not a non-linear calculations models. More techniques for direct manipulation, more touch-enabled devices, and also develop this demonstrators here for using conceptual design. And what I want you to take with you when you design application, try to see if you can make your applications more immediate. I mean, your models are quite not so complex. And see if you need a calculation step. Can you do, if you change a number, can it calculate automatically? So that you don't have this kind of enter your parameter, press execute, wait, and display. So that's something you can think about if you, in the future you design your user interfaces. Do you really need a computational step? Can we do it in the background? Can we do it immediately? Can we visualize it directly? Because the applications become more interesting, explorable, iterative, works more well in the design process. So just have that in mind, and I also give you kind of intro to what you can expect. And I hope also that you get some insight from Pierre, how it is to develop real applications as well. So thank you.